Okay, so moving on in this presentation or in this video, we will be talking about now mixed effects models and sort of rethinking what they mean. What does it mean to have population level parameters? What does it mean to have random effects? Why do we maximize the marginal likelihood? These questions that perhaps you may already know something about from working in pharmacometrics or working in nonlinear mixed effects models. But actually turns out these are much more general concepts than some of the model structures that we often work with in this field. And so we're going to take a look at some of the sort of more generalities or the generalizations of the concepts that we already perhaps familiar with. So first, let's maybe take a look at what a mixed effects model is, or a nonlinear mixed effects model, perhaps if your model is nonlinear. So such a model has generally something called population level parameters. So we have data from multiple subjects or multiple images, let's say, if it's image data, or multiple individuals in general, perhaps in a population. And so we have this sort of hierarchical nature of the data where there are some parameters that are shared between all the subjects. Often we call them theta or population level parameters, and a subset of those parameters are often called fixed effects. And then some other parameters are subject specific, and they're often called random effects, or they're modeled as random variables, and they're given the name random effects. And then we also have covariates that are subject specific, and a response that's also subject specific. And so if we have three subjects, for example, we get something that looks like this. And the idea is that this theta here is a population level parameter. It's often modeled as a deterministic variable as well, or deterministic quantity, although not necessarily. Sometimes we also give it a prior distribution and model it as a random variable. But typically it is modeled as deterministic quantities, or in traditional pharmacometrics models, these are modeled using or as deterministic variables or parameters. And they're shared between all the subjects. And so the theta here is shared between subject 1. So this block here is for subject 1. This second block is for subject 2. And the third block is for subject 3. Now, for subject 1, we have some parameters in theta. They affect the prior distributions on the random effect. And so the prior distribution on the random effect, traditionally, again, in pharmacometrics, would be something like a normal distribution with mean zero and some covariance matrix. And the covariance matrix would be a population level parameter that's shared between all the subjects. And so the covariance matrix here would be part of theta. And so theta affects the probability distribution of eta1 through that covariance matrix. It's also the same covariance matrix for eta2 and the same covariance matrix for eta3. Now, eta1 plus the remaining variables in theta, so everything that's not the omega, like the sigma, for example, and any other, like any residual variability parameters or any other coefficients, for example, that you might multiply the covariates with, or the typical value of clearance, typical value of volumes, all these parameters that we typically model as population level parameters, they affect the probability distribution of the response. So the probability distribution of the response will depend on those population parameters, but also will depend on the random effects. And the random effects are usually parameterized or modeled as the deviation from the typical value. So you would think of the typical value for clearance would be a population parameter, and then an individual's deviation from the typical value, which could be either positive if the person has clearance that's higher than the typical value, or negative if the person has a clearance that's lower than the typical value. This deviation would be considered an individual parameter. And so that also comes into play or affects the probability distribution of the response for that specific individual. And of course, we have the covariates, which could also come in if we have a covariate model. And generally, if you have time, for example, time would be considered sort of a special covariate here that comes in here as well. And so that's the overall or the general structure that we typically work with, where we have population level parameters theta, we have random effects, one set of random effects for each subject. So these are actually different parameters. Often people don't distinguish between whether they're the same parameters or different, like are they just different values for the same parameter? But actually it's best to think of them as different parameters. Eta1 is different from eta2, different from eta3. They just happen to come from the same distribution. They happen to have the same prior distribution. Right, but their posterior might be different. So when you fit the values to each model, or when you fit this model here, the individual model, to each individual's data, you get very different values for eta 1 versus eta 2 versus eta 3, depending on the response and the covariates. But it's good to think of those as basically a separate set of variables. Now, even though in modeling we usually just write one line of code to define all this batch or all this group of random effects. And so what that looks like in a Pumas model, if you define a Pumas model, we often have these blocks, basically. And this here is the param block, which is where we define all the population level parameters. So that includes things like traditionally what we call theta and omega and any other parameter like TVCL and whatnot. This is a dummy model, so this is not necessarily a real model that's used. But here in the param block is where we define all the population level parameters theta. Now in the random block, this is where we define the random effects prior, or the prior distribution of the random effects for all the subjects. So this here, we just write eta, we don't write eta I or eta 1, 2, 3, but it's implied that this actually, there's one random block or one set of random variables for each subject. And so eta 1 would be a multivariate normal with mean 0 and covariance matrix omega. Eta 2, same thing. Eta 3, same thing. Right? And so here we just write eta, but it's implied that this is subject specific. And then we have the covariates block where we specify the covariates x. And as I said, there is an implicit covariate as well, which is time. We don't often write it explicitly here, but it's sort of carried with us the whole time, and we can use it in different parts of the model as we are writing this model. And then everything after the covariates block is basically distribution of y given all these other three quantities. So we are allowed to use theta here, we're allowed to use any part of theta, we're allowed to use any covariates here, and we're allowed to use any random effects. And then at the end, we define the distribution of the response. The response here is called dv, which is our yi. But again, it's implied that everything after the param block, everything else is subject specific. So the random block is subject specific. The covariates, obviously each subject will have different covariate values. And then the pre-block and the dynamics and derived, they're all sort of subject specific. And so this here is basically yi for a specific subject. And it's a normal distribution with mean equal to this value here, the concentration variable, and then some proportional error model. And the concentration is given by the solution to the ODE and some other parameters. And so everything after the covariates block is the probability distribution, or the function that describes the probability distribution of yi for any specific subject I, given theta, their corresponding eta I or random effects, and their corresponding covariates xi. So that's how you normally write it. We drop the subscripts for the individuals, but it's implied that this is shared between the whole population and everything else is individualized. Now let's discuss the likelihoods and what does it mean. So in general, the likelihood of a model, or the likelihood of the parameters, is the probability of the data given the parameters. And so we can say the same, like we can refer to the same quantity in two different ways, either as the probability of the response given a set of parameters. So let's consider these two parameters. So it's the probability of y given theta and eta, if we ignore x for now. Or we can say it's the likelihood of theta and eta given y. So both are exactly the same thing. So the likelihood is a property or is a function of the parameters, but it's equal to the probability of the data, the observed data, given those parameters. Right? And so when we maximize the likelihood, we're trying to maximize the probability of having seen what we see, or what we saw. So what is the probability of observing what we observed, right? And then trying to maximize that, and that's sort of the intuition behind it. And this is, again, often called the likelihood in general. But there are different types of likelihoods in the context of nonlinear mixed effects models. You could either write the conditional likelihood, or something called the marginal likelihood. And this really refers to how we treat the random effect. So how we treat this variable eta here. And again, think of this as a specific individual. So this is actually eta I, this is actually xi, but we're talking about a specific individual now, just zooming in. And so the conditional likelihood is the likelihood of the pair of parameters theta and eta. So the pair of parameters, the population level parameters, and the random effects for that specific individual. The marginal likelihood, we take this eta here and we multiply it or we integrate it out. So we take the average, basically conditional likelihood, weighting the each conditional likelihood by the probability of the specific eta. So if eta equal 1 has a probability or a PDF of 1, and eta equal 2 has a PDF of 0.1, and so on, then we take the corresponding conditional likelihood for each value of eta multiplied by the probability density function or the probability density of this specific value of eta according to the prior, and then we just take the average or the weighted sum. And so if the way we write this in a continuous way or in a continuum, because eta here is a continuous random variable, is using this integral. But the integral is basically just a fancy way to say that we are sampling values from the prior, let's say, or it's equivalent to saying that we are sampling values from this prior. So sample a lot of eta values and then take the average of this here according to the samples of eta. So that's sort of the idea here. And so we can again take the average conditional likelihood across all these different eta values, and that gives us the marginal likelihood. Now that might seem like an arbitrary thing to do. Why are we doing this? Because let's say for each individual, some values of eta might be more likely than others, and so this might not seem very intuitive as to why we're actually doing this kind of weighted average or this kind of average here by sampling from the prior. And so let's dig a little bit deeper into what this means. Now, the goal with usually the reason we care about the marginal likelihood is because it's the main objective function value when fitting these nonlinear mixed effects models. And so it's important to understand why this is, and we're going to provide some insight into that in the next few slides. But traditionally also you could have fitted basically using the conditional likelihood. Or one valid question to ask is, why don't we just maximize this quantity here? Why do we actually have to marginalize? And so the idea here is like we could just fit the theta values, we can fit each of the individual's etas to their corresponding response, and we could just directly fit this conditional likelihood instead of the marginal likelihood. And the answer to that is that this actually can cause horrible overfitting problems because we end up having too many parameters. And the marginal likelihood actually penalizes overfitting in a way, and we will see again how that is. So one way to look at the or like let's maybe take these three examples of models. So there's model 1, model 2, model 3, and we have this joint probability versus random effect. So what's the joint probability? The joint probability is this product here. And so the marginal likelihood is basically the area under the curve of the joint probability. So when you take the integral of a function like this with just a single output, the integral has the interpretation of being the area under the curve from minus infinity to that point that you took the integral to. And so the integral, for example, of random effect equals 1 is the area under the curve. For the blue curve, for example, is the area under the curve from all the way from minus infinity, or minus 2 in this case because it's pretty much 0 beyond that, all the way up to 1. So that area under the curve is precisely what this marginal likelihood is. And so to visualize the marginal likelihood, it's useful to actually plot this joint probability curves. And so let's take three models with these three joint probability curves, and let's try to make sense of what their area under the curve looks like. So in these cases here, in these three models here, which of those models has the largest area under the curve? Now this model has the largest peak, but it doesn't necessarily mean it has the largest area under the curve. Now, largest peak could mean that, for example, this value here is very, very large for a specific value of the prior. So let's say eta equals 0, or eta equals, in this case eta equals 0. This gives us a very, very high value of the conditional likelihood, and so we have a large peak. We have a very high peak here. However, the conditional likelihood is quite sensitive to the choice of the random effect. So if I change this random effect from 0 just maybe to +1, then all of a sudden I have 0 here, and so, or something very close to 0. And so that means that perhaps, let's say the prior here doesn't fall very sharply. Let's say the prior here folds nice and smoothly. But this here probably fell very, very sharply, going from eta equals 0 to eta equals 1. And that's why the product of them is pretty much 0, right? And so when the conditional likelihood is extremely sensitive to the value of eta, we end up getting this kind of peaky behavior where we have a peak and then we fall off the peak straight away or quickly as soon as we move away from that peak. And that implies that the conditional likelihood, assuming the prior is not the cause of this, that the conditional likelihood is quite sensitive, and therefore like maybe we got lucky and we found this super good value of eta, or maybe we are overfitting the data in some way. And actually overfitted models tend to look like this. This is not necessarily like a symptom or a guarantee of overfitting, but overfitted models tend to look a lot like this, where we have this sort of peak, and then if we move slightly away from that peak, then the likelihood drops pretty quickly. So this is a typical phenomenon with overfitted models. Now, on the other hand, this model here has a lower peak. So it doesn't achieve the same sort of heights as in the joint probability. However, it does have much less sensitivity towards the random effects. So a lot more values of the random effects are actually giving us good conditional likelihoods. And so know that in practice, we don't actually know what the specific value of random effect is, because often we don't really have enough data, and so to identify what the specific value of eta is. And so being less sensitive to the value of eta actually does give us a little bit more robustness towards this lack of knowledge. So if you don't know exactly what eta should be, well, in this case, maybe it's 1.1 or 1.2, but also if we say 1.3, it's probably not that bad. And so not being too sensitive to the value of eta actually gives us a little bit of robustness in the model. And that robustness also translates to lack of overfitting. So models that are not overfitted tend to have this robustness property, that moving away from the optimal value of eta doesn't cause sort of a very sharp drop in the performance of the model. And so clearly the model with the largest area under the curve is the blue one in this case. And that basically translates to being the model with the largest marginal likelihood, or the marginal probability here. Now, in general, a good model, or what we're looking for, is a model that has a high peak, which means that the best model possible, the best value of eta possible, achieves a high joint probability of the parameters and the data. Assuming the prior is not too influential, then that means we have a high likelihood. So this value here is quite high, but also the value should not be too far from the center of the prior. So the value of eta ideally should not be like minus 100 or something like that if the prior is a normal distribution with mean 0 and standard deviation 1 or something along those lines. And so the prior should also not be completely violated, or you should not be too far from the center of the prior. But more importantly, because we tend to optimize the prior is something that we can optimize when we're fitting towards the model. And so maybe more importantly is actually the conditional likelihood for a specific value of eta has to be also quite high. So we want a model that has a high peak, but also we want a model that has a wider base, and that makes it less sensitive to the value of the random effect. And again, that's typical phenomena or a typical symptom of a model that's sort of a healthy model, one that's not overfitted to the data, perhaps. Now, that's the intuition, but there's actually more mathematical sort of rigor that we'll come into in a minute. We'll go to in a minute. And so, intuitively, if a model is able to fit the data well, it's not a good model if it's very sensitive to the value of the random effect. Right, so we want a model that's able to fit the data, but also not extremely sensitive to the value of the random effect. And models that are good but sensitive, they tend to be overfitted. So that's the intuition behind the marginal likelihood. Now let's look at a little bit more math to understand what is this quantity actually measuring. And so in this case, or in this slide here, we consider a single subject I, and the marginal likelihood of this subject. So now we brought back the subscript I here for the equations. And so the marginal likelihood of theta is the probability or the marginal probability of y given theta. Because again, probability is always of the data, but then, or of the main variable, but then the likelihood is always of the parameter. And so this is the marginal likelihood of theta, or the marginal probability of yi given theta. This is the same quantity we had before. It's just the conditional probability here, or the conditional likelihood here. multiplied by the prior of this random effect, and then we integrate over a to I. So that's again for a specific individual I, and so we're integrating over this random effect for that individual. Now, this is how we normally write the marginal likelihood. Then we go and try to approximate this and try to optimize it using the Laplace method. So this is typically how we compute the marginal likelihood, or this is the first step at least. And then we go and approximate this here, or the log of this, using some second order Taylor series expansion or approximation. And then we can approximate this. So that's useful when we're computing the marginal likelihood. But there's another way we can write the marginal likelihood that's more useful when interpreting the marginal likelihood or when making sense of it. And so one way to write it is using this sort of like chain rule or product rule for the probabilities. And so the probability of yi given theta, and here in this case we assume that yi is a time series response. So let's assume that yi for a single subject is actually 10 observations, not just one. So we have an observation at time 0, time 1, 2, 3, 4, etc. And then let's take or consider one observation at a time. So first consider the case when we haven't seen any data before, right? And so when we haven't seen any data before, that's the case here of j equals 1. So when j equals 1, this value here is j minus 1 is 0. And so basically that means we are conditioning on having seen nothing yet. And so when the interval here is 1 to 0, that means that's null, basically, or we haven't seen anything yet. And so it's the probability of the first observation. So this here is the first, j equals 1, meaning this is yi1. So that's the probability of the first observation at time 0, let's say, given the population parameters, right? And so that's intuitively, again, the average probability across all of the random effects. So that we'll have to average across the random effects later. But for now, let's just intuitively think of it as the probability. Let's ignore eta for now. Let's just think of theta. So it's the probability of the first observation having seen nothing yet, given the population parameters, times, then we multiply it by the probability of the second observation having seen only the first observation. So when j equals 2, this is 1 colon 1, and so this means that we've seen the first observation already, and then we're asking what is the probability of the second observation having seen the first one. Now when j equals 3, then we have seen 2 observations, and we're asking what is the probability of the third observation having seen 2 observations already, and so on. And so as you keep increasing j from j equals 1 to the number of observations per subject, or this is the number of observations for this particular subject, we see the pattern here. So the pattern is always what is the probability of the next data point or the next observation for this subject having seen the previous observations for this subject. Right? So having seen nothing, what's the probability of the first observation? Having seen one observation, what's the probability of the second? Having seen the first 2 observations, what's the probability of the third? And then we multiply all these probabilities. And so that's a very important intuition, because it's basically the probability or the average probability of the next unseen observation. Right? The marginal likelihood is the average probability of the next unseen observation in this case. And so that's precisely what sort of the concept of generalization is all about. Like, I want a model that doesn't overfit. What's the definition of a model that doesn't overfit? Is a model that's able to predict the future that's not seen yet. And so here I'm formulating this directly as in the marginal likelihood, or the marginal likelihood encodes this notion directly as which is the probability of the next observation given all the previous observations across all possible observations. So as you accumulate observations, we just average all those out. Now, ideally, a model that has a high probability of the next unseen observation given all the previous observations for all of these observations for that subject, that's a pretty good model. So that's sort of intuitively, again, what the marginal likelihood is measuring. But it's not just intuition, it's actually exactly the mathematical quantity that it's measuring. It's exactly this notion of the probability of the next observation given all the previous ones. Now, I haven't included eta here because eta is not too important. We're just worried about the population parameters. But to actually compute any one of those, you would have to marginalize the random effects as well. So you'd have to then bring in the random effects, because we don't really define this directly. We in our model, we define the conditional likelihood. We don't actually define the marginal likelihood. And so we define this and we define this in our model. But to compute each of those terms, we still need to marginalize the random effects. But at least conceptually, this likelihood here, or the marginal likelihood, can be written like this. Now, let's consider the case again where j equals 1. So this is just an unrolling of that. So when j equals 1, again, we've seen that it's the probability of the first observation having seen nothing. So this is here the case where we've seen nothing at all. So 1 to 0 is just null. And then that's just this probability here, probability of the first observation given theta, and then we bring in the random effects and integrate that and integrate it out. And so we still need to marginalize the random effects, but at least intuitively you can think of it just as the probability of the first observation given theta. And again, the way to compute this, let's say one way to actually compute this is to sample all possible values of eta from the prior. So we take this prior distribution of eta, sample a lot of values, maybe 1,000 values or 10,000 values, and then take the average probability of the first observation, right? So we're saying that the prior should like almost all of the prior, or samples from the prior, should all fit this first observation pretty well. Not just one value, not just one specific value should fit this first observation, but the entire prior should fit this first observation pretty well. Now, in the case when j is more than 1, then we have some observations here. So in this case, actually, instead of the way we marginalize the random effects is not using the prior, but it's actually using the posterior distribution. And so the way we marginalize the random effects is we take the conditional likelihood here of the observation that we care about, the jth observation, given the random effects, given the population parameters, and then multiplied by the posterior distribution of the random effects given all these previous observations, and that's what we take the average or the integral of. And again, intuitively, what that means is, let's say we observe two observations so far. We can do MCMC or any kind of procedure to sample from this posterior here, so we can get what are all the possible values of eta I of the random effects for this particular individual that are consistent and compatible with those two observations that we've seen so far. Right, so that's a valid question to ask. What are all the possible values of eta that are consistent with those two observations we've seen so far? And so now we're not really interested in the entire prior being good or being able to fit the next observation, but just the values that are consistent with all the previous observations. So I would like all the values of eta that were consistent with the previous observations and were able to fit the previous observation to also be able to fit the next observation. So it's a pretty reasonable thing to want, right? All the values of eta that were able to fit the previous observations, ideally they have also good predictive performance where they're able to fit the next observation well. And so by sampling from this here and then taking the average of this conditional likelihood or the probability of the jth observation, using all those samples, that gives me this sort of idea that I would like to enforce, which is that all the values of eta that are possible given or probable or likely given the previous observations, those should also ideally have a good probability for or a good likelihood for the next observation, right? And so again, this is the notion of generalization, or being able to predict the next data point well, given all the previous observations. So hopefully this is kind of clear, but if not, we have the office hours and we can discuss. So again, intuitively, the marginal likelihood is a desirable property to optimize because it encodes this notion of generalization. It encodes this notion of being able to predict the next observation from all the previous ones. So you take the previous ones, you fit your individual model, get the random effect values, and then you want that value or those values of the random effects according to your posterior to also have good probability or good likelihood for the next observation. And that notion is quite important. Now compare this to maximizing the conditional likelihood directly. So if we just maximize this conditional likelihood here and all of the random effects are maximized sort of jointly, then we're not really building in or encoding that notion at all. This is just like we're throwing in a whole bunch of parameters at the model and fitting all of them, and you're not really encoding generalization anymore. And so by integrating the random effects, what seems like an ad hoc sort of thing, let's just take the average for all the random effects, turns out it actually has a pretty significant and meaningful intuition behind it, and it does actually end up encoding this generalization performance as part of it. So perhaps go through these slides again, try to make sense of the notation and the math, and then if it's still not clear, then we can discuss during the office hours. So in Pumas, we have quite a few algorithms that can be used to fit models, to fit nonlinear mixed effects models in general. And so these include things like FOCE and Laplace and FO. So these are all specific algorithms for maximizing the marginal likelihood. Now, sometimes you have a prior distribution or regularization on the population level parameters. In the case of DeepPumas, for example, we usually have these L1 or L2 regularization on the population parameters. And so we need to use map FO or map FOCE or map Laplace. Map comes from maximum a posteriori, and so that's when we have a prior or some regularization on theta, we need to actually use the map version of the algorithm. But when we want to ignore the prior, or when we don't have a prior in the model or regularization, we can just use FO or FOCE or Laplace directly. Now, we also actually have a way to optimize the conditional likelihood. So if you want to optimize the conditional likelihood plus some log prior, so usually the prior and the random effect is actually considered as well. So it's not just the conditional likelihood, but also we add to it the prior on the random effects here, but without integrating. We don't marginalize. But let's say the joint or the sum of the log conditional likelihood and the log prior of the random effects, we can use this joint map functionality or joint map algorithm. And if we have prior on theta, this will be taken into account. But if we don't have prior on theta, then basically this will be the conditional likelihood plus the log conditional likelihood plus the log conditional prior of the random effects, but without the population parameters prior. So this is actually incorrect. This should be the joint probability of the data and the random effects that's actually being maximized. And so we will fix this in the slides. But the idea is that, again, if you want, you can add regularization or prior and theta, but it's optional. And if you don't, then it will just be ignored or it will not be considered. Now, why do we have this joint map method? We just spent a few minutes or a few slides explaining why the marginal likelihood is what we want to optimize, why it encodes the generalization performance and all these nice properties. So why do we still have a way to optimize this in Pumas? Now, this is in very special circumstances. You can do this, or you can use this as an optimization technique or as a fitting method, in particular in two scenarios. One is if you're just developing your model and you want to see, is this model flexible enough or not? So you're not really worried about overfitting yet. You're worried about underfitting. You're worried about, is this model the right structure? Is it able to fit my data or not? And so for that, I don't really care about marginalizing and maximizing the marginal likelihood. I just want to see, okay, for each individual, am I able to overfit or not in the first place? Because it's possible if the model has not yet been perfected or if the model is still incorrect, maybe I'm using a one compartment model when I should be using two, or maybe I'm using one random effect when I should be using three. And so in those cases, the model might still be underfitted. And so just by fitting this quantity here, I should be able to actually notice this. I don't need to fit the most sort of correct or the most appropriate objective function value to notice the issues with the model. And fitting this is much more quickly or much faster than fitting the marginal likelihood, because the marginalization is actually a bit of a pain to go through or to compute computationally. And so to approximate this marginalization or to perform this marginalization, it often takes a lot more time than to just fit the conditional likelihood, perhaps plus some prior, log prior, or times some prior distribution for the random effects, but without marginalizing. So it'd be basically maximizing this here, and then the product of this for all individuals, basically, but then without the marginalization part. So that's the first scenario when using this joint map approach where we maximize the integrand essentially directly and not the full integral. And so that's equivalent to finding the model with the largest peak, right? But if the largest peak is not even that large, that tells me all I need to know at this stage of the modeling. So when the model development is still ongoing, perhaps if the largest peak is quite small, then that tells me the model is pretty bad. I should go back and try to make the model more flexible to fit the data better. But once I have a pretty good peak, and I have the individual fits are pretty good, but then the area under the curve is pretty bad, that's when I can go back and now fit the marginal likelihood and maybe worry about the prior distribution or the probability distribution of the random effects here, and I may need to tweak this. And that brings me to my second scenario. So the second scenario where joint map might be useful is if you have a very complicated model and a lot of subjects, and fitting the marginal likelihood is just too slow. And so it's possible that when you use this, like the FOCE or Laplace or any other method for fitting the marginal likelihood, it might be way too slow and painfully slow, that it's just infeasible. And so in cases like this, having sort of two steps or fitting the model in two steps is something that we've had good success with in the past, where the first step, we try to just find good values of theta and good values of eta. And that's mostly in the context of sort of DeepPumas models or models with neural networks, because those tend to be the most expensive. Those tend to be the worst offenders. When we have this theta here is quite high dimensional, and even sometimes eta is quite high dimensional. And so in those cases, what we can do is actually fit this first. So try to find the model that has a good peak first, a high peak first. And then we can actually try to tweak the prior or figure out ways. So this model generally will need to maybe more heavily regularize it. And so we might discuss this separately, but this needs special regularization to make sure we don't overfit too badly. But then after we fit with joint map, what we then try to do is try to find a good prior that would then enable the area under the curve to be higher. And so we try to go back and then we take a look at, given the value of theta, what are all the possible values of eta, or what's the posterior distribution of eta, and then we try to find a good prior correction. So we find a new prior distribution that's then able to fit all these posteriors. And so we do almost like two-stage fitting, where the first stage we just try to get good iPreds, try to get good predictions, and then in the second stage we try to get good generalization performance, and we try to actually get a model that maximizes the marginal likelihood. So first we're trying to maximize the joint probability here, and then the next step we try to maximize the marginal likelihood. And we've had luck with this in cases where the model is very expensive. It is quite fiddly. You need to make sure that you regularize the thetas quite well in the neural network so that you don't horribly overfit. And then you need to do MCMC to get the random effect posteriors after you do the first fit. And then you need to fit usually something like a normalizing flow or any kind of, maybe you could also use a Gaussian distribution to fit all the combined posteriors. So it's almost like doing a step of expectation maximization in that sense. And there is a talk by my colleague Lorenzo Quintento on part of this workflow, which is the prior correction part. And so if your model has good iPreds, but the prior is misspecified, the VPC looks really bad, then there are certain things you can do or certain techniques that you can perform to correct the prior distribution or to learn the prior distribution that would actually fix your model, essentially. And so when you fit this, or when you maximize this, you are basically maximizing for the performance of your iPred. You want your individual prediction to be as good as possible. But then you don't really care about the simulation performance being that good. And the step that Lorenzo is discussing on his video, which you can find in our YouTube channel, the Pumas AI channel, that shows you how you can then correct the prior distribution. Now, the prior distribution correction can also be done in other contexts where we might be fitting the marginal likelihood, but the prior is misspecified somehow. And so maybe we have multiple modalities in the prior that in the real data, but then those are not modeled in the prior, and then we can also try to fix those issues with the prior distribution using the same normalizing flow technique. And so this normalizing flow and prior correction technique is useful beyond just this use case here when we use basically an improper objective function value. So this joint map is not a proper objective function value in nonlinear mixed effects models. We should not generally use it, again, except in those two very special scenarios. The other case when we can use this is if we have too many observations per subject, that the posterior distribution for the individual is basically almost a point estimate. Then in that case also you can use joint map. So that would be the third but very rare scenario, because usually we don't have that many observations for a subject. And so if we have too many observations and not many random effects, and the random effects are all nicely identifiable, then you can also get away with using this joint map approach. But let's say 99% of the time, you're probably going to want to go with the marginal likelihood, except again, if you're doing model development, then you can start with this and then switch to this. That would be my recommendation. So mathematically, the FO, FOCE, Laplace, and even SAM or any kind of EM algorithm try to maximize the marginal likelihood. So this is the marginal likelihood here of theta given this yi, or given the observation y, and then we're taking the product of the marginal likelihoods for all subjects, and then we're maximizing with respect to theta. So we're maximizing the population parameters. Now each of those includes an integral. Each of those includes some integration over the random effects as well. And then as a post-processing step, after we get the maximum value of theta, or the population parameters, sometimes also to get the individual predictions, we do a second optimization to maximize this integrand. So now we maximize the thing inside the integral, but for each individual. So this quantity here inside the integral, we maximize it, but for each individual, and by fixing theta. So we fix the value of theta, and we only maximize it with respect to eta. Now that's okay, because that actually gives us the mode of the posterior distribution for that specific individual. So what is the best value of eta that fits my data, having already fixed theta? So having already figured out what theta star is, I'm fixing theta star here, or theta to theta star, and then I'm maximizing over the value of eta I, or over the value of the random effect, to find what's the best value of the random effect that fits my data. Right? And I'm using this prior here as some sort of regularization, because I don't want to deviate too much from the population. I don't want to have eta I be equals 1,000 or minus 1,000, right, or something like that. If the prior is sort of densely is densely distributed around 0, so I don't want the value of eta to be extreme values, but I still want sort of the best value of eta that's not too extreme, that fits my data. Right? And that's the mode of the posterior distribution of eta I given all the observations yi that we have. So that would be the mode of this posterior here. So if we've seen a posterior like this here, where basically we have all of the observations, so j equals mi plus 1. So having seen all of the observations, the posterior distribution of eta, the mode of that posterior is essentially this value here, right? So the reason this is useful is because when we plot the individual prediction, this is actually what we use to plot the individual prediction. Like we plug this in here, and then we get the mean of this distribution, usually if it's a continuous random variable or a continuous response, or the mode if it's, let's say, a nominal categorical discrete response. And so we get the IPRED based on this value of the random effect. Now the difference between the FO, FOCE, Laplace I, SAM, etc., and the map version of that is that we add an additional term here to the first optimization, which is the prior distribution or an additional regularization term on the population parameters. So that's outside of this whole integration mess. So it's just on the outside here, we add this additional term and then we maximize. And that changes theta star, but it will not change the procedure for getting eta. So obviously, once theta star changes, etas might also change, but the procedure is the same. So the eta star computation is exact same in the first line, in the first row, and the second row. The only difference, again, is just we added this additional prior term in the objective function value when maximizing the population parameters or when fitting the population parameters. Now, in contrast to this, in joint map, we actually maximize the joint probability or the joint probability of actually, this is the posterior distribution, so that's the joint posterior of the population parameters and all of the random effects for all of the subjects. So this eta here is actually not for a specific subject, but for all of the subjects. So eta would be made up of eta 1, eta 2, eta 3 for each individual. And so this is actually, if we have 10 subjects and then 2 random effects per subject, then this is 20 parameters here in this eta. And then on top of that, we also have the population parameters. And so when we maximize the joint posterior of theta and eta, given all of the observations, then that's basically the joint map solution. And to maximize this, it's equivalent to maximizing the joint probability of theta, the random effects for all the individuals, and the observations for all the individuals. So it's the joint sort of probability between all of them that we're maximizing. And so this here would be the regularization term for the population parameters. This, you can think of it as a regularization term for the random effects. And then this is the actual conditional likelihood. That is the main part. This is sort of the main driver of this whole objective function value, which is the conditional likelihood for a specific individual. And we multiply the probabilities for all the individuals together, right? Now, when we maximize, typically we take the log of this and actually maximize the sum of the log of these quantities here. But it's the same thing, because log is a monotonically increasing function, so maximizing the log of something is the same as maximizing the quantity itself. Of course, the quantity has to be non-negative and strictly positive. But in any case, the difference here, as you can see, is the integral. So here we had the marginal likelihood, and that includes an integration, whereas in the second case, we don't have the integration. We actually directly maximize the product of the conditional likelihoods times also some regularization or the prior and the random effects, but there is no integration happening here. There's no integration going on here. Now, another fitting method which we haven't discussed so far is actually using something called MCMC, or Markov chain Monte Carlo. And the idea here is, instead of finding just the mode of the posterior, so finding the mode of the posterior here is not the best thing to do for the reasons we mentioned, that it's more prone to overfitting and we have too many parameters and so on. However, if you actually sample from the joint posterior, that can fix this issue. That's actually a valid thing to do, and that's a good thing to do. The problem is that in many cases it can be expensive to actually sample from the entire posterior, especially if you have neural networks in your model. And neural networks actually complicate the Markov chain Monte Carlo or the MCMC sampling, and make it quite difficult to actually converge to the true posterior if we have neural networks. But in more traditional models, when we don't have neural networks, that's actually a perfectly valid thing to do, is to just go ahead and sample from the whole posterior, the joint posterior for theta, and all the random effects. And this will not have the same sort of overfitting problems that joint map has. So this is still a perfectly valid thing to do. But in the context of DeepPumas, we're not going to see this very much, except in some cases we will see it when we actually fix the value of theta, or fix most of the values in theta. So maybe fix any neural network part of theta, and or even the entirety of it, and we just want to get the posterior distribution of the random effects given the observations. And so in that case, we have seen uses for this particular case, or these particular cases, the two cases where we fix most of the parameters of theta, or we fix all of the parameters in theta, and just we're interested mostly in the posterior of these random effects here. And we use MCMC for that. And so this is the last slide in this presentation, but I wanted to go back and also discuss a very important concept, which is what does it mean to have a random effect? And we see that in many cases in Pumas, the random effect or nonlinear mixed effects models, the random effect is basically a deviation from a typical value. So the typical value of theta here is sort of a population parameter, and then the random effect eta 2 is some deviation from the typical value. Could be additive deviation, could be multiplicative deviation. So if it's more than 0, we multiply by the exponential of it, and that gives us something greater than theta, or greater than the typical value. And if it's less than 0, then the exponential of that is less than 1, and then by multiplying the typical value by a number less than 1, we get something less than the typical value. So it's still deviation from the typical value, but it could be additive or multiplicative. But actually, in nonlinear mixed effects models or in DeepPumas, one way to think of these random effects in general as just as individual degrees of freedom that we can freely optimize. So they don't necessarily have to be used as deviations from typical value. You don't necessarily have to assign a meaning to them. Essentially, you can just use them as inputs to a neural network to individualize the output of that neural network, right? So you can more generally think of a random effect as just an individual degree of freedom that a neural network may be able to use in any way that it sees fit to fit the data well, to find a good fit of the data, to find a good model that's able to generalize well to future observations, maximize the marginal likelihood, etc. And so the random effect does not really have to have that specific meaning that we usually assign it in pharmacometrics. It can be a much more general quantity than that. And that's important to keep in mind, especially in some of the tutorials that you're going to be working on after this presentation. So keep that in mind. It's a very important notion. It's a very good thing to conclude this talk with, just to keep that sort of fresh in your minds. And thank you for your attention.